Hello and welcome to this presentation, Typology Meets Data Mining, the German Gender System. My name is Sebastian Feddem. My co-authors, Matías, Guzmán, Naranjo and Greville, Corbett, are very happy to have the opportunity to present our joint work to you today as a keynote in the general session of this year's SLE meeting. In recent years, linguistic typology has increasingly profited from computational methods. The hope is to discover patterns in large data sets more quickly and more accurately than would be possible for a human researcher. This is commonly known as data mining. A linguistic system which could benefit from such an approach is German, which arguably has the most complex gender assignment system in the world. We begin with a brief look at the typology of gender assignment and the question, what makes German so special in this respect? We cover the essentials of how gender assignment works in the language, and we talk about data mining, our data and our methods. We then discuss the results, including nested generalizations, where combinations of criteria make certain predictions which neither of the individual criteria are capable of making on their own. Finally, we offer our conclusions. In the typology of gender assignment, we distinguish between semantic systems on the one hand, where knowing the lexical semantics of a noun gives us its gender for all or most nouns, and semantic and formal systems on the other hand, where we also need morphological and or phonological principles. German fits here, being semantic and formal with both morphological and phonological rules. German has a bit of a reputation for being difficult and having extremely complex gender assignment principles. In a recent compilation from the literature, we find 378 semantic and formal assignment principles, some in conflict with each other. And we know, of course, that children learn the system and their intuitions about gender assignment are remarkably consistent between speakers. And German has only three values: masculine, feminine, and neuter, for which we will consistently use the colors blue, red, and green. So this looks easy. There are many systems with more gender values. But the German gender system is notorious for its complex tangle of interacting semantic, morphological, and phonological assignment principles. Previous work, notably by Klaus-Michael Köpke and David Zubin, has demonstrated clear regularities in the assignment of gender to German nouns in terms of semantics, phonology, and inflection. So on to the essentials of German gender assignment. First, we have the basic semantic assignment principles. Sex differentiable nouns are assigned gender on the basis of sex. Frau and Kuh are feminine, Mann and Bulle are masculine. For most nouns, we need morphological principles, compounding, derivation, inflection class, and phonological principles, stem shape. An important morphological principle is the last member principle, or Letztgliedprinzip, which says that the gender of the whole word is determined by the gender of the last element. Mutter is feminine. Schutz is masculine, so by the last member principle, the compound Mutterschutz is masculine. Derivational affixes are associated with a gender value which is assigned to the derived word. And this is irrespective of the gender of the base, if it is a noun. For example, the suffix schaft derives feminine nouns. So we get die Freundschaft, friendship, and die Landschaft, landscape, from the masculine noun der Freund and the neuter noun das Land, respectively. The way a noun inflects is also important. For example, nouns which inflect like Lampe with the genitive singular in 0 and the nominative plural in n are all feminine. These two principal parts here, the genitive singular and the nominative plural, are given in orange. For at least 4 inflection classes, gender can be predicted unambiguously or nearly unambiguously. Often, partial prediction of gender is possible. For example, Knopf, button, cannot be feminine based on its inflection. There are no feminine nouns in its inflection class. Phonological cues can help when distinguishing masculine from neuter nouns. 64% of monosyllabic nouns are masculine, and 93% of monosyllabic nouns with initial kn are masculine, the only exception being the neuter noun das Knie. So for Knopf, this points overwhelmingly to masculine, which indeed it is. Such phonological assignment principles have been studied in detail by Zubin and Köpke, but we need to remember that none of them is exceptionless. The diagram, which you will see in a second here, will give a taste of how these different semantic, morphological, and phonological principles of predictors overlap and form intersecting sets. The nouns in this set here are feminine due to their semantics. The nouns in this set are feminine due to the way they inflect. Notice how an intersecting set is created. Finally, we have these nouns in this set, ends in schwa, again, intersecting with the previous sets. However, they're non-feminines in this set. Zeuge, witness, is taken care of by a different semantic principle, and Ende, end, is at least not feminine by the way it inflects, and there will be more about Ende towards the end of our talk. Now I'll pass on to our data and methods. In analyzing the German gender system, there are at least 3 pitfalls. 1, cherry picking. Observations of alleged regularity are sometimes based on few examples, and the overall applicability of these regularities is left unexplored. 2, often we find generalizations without a baseline. Thus, a prediction of a particular gender value for, say, 45% of the nouns is hardly remarkable if 45% of the nouns overall are of that gender. And 3, missing the importance of overlapping factors. Phonological, morphological, and semantic properties may make the same gender value more probable. So we have to be careful about making a claim for a particular generalization, and we need to investigate overlap as part of the system. So here we're taking a more holistic view. For this, we mine a database of more than 30,000 German nouns from WebSelex based on the Mannheim corpus, coded for gender, phonological shape, inflection class, and derived compounded status, which we've cleaned and to which we've added semantic information, human, animal, object, abstract, mass, and frequency based on the larger cowl corpus. Given the complexity of the system, it's very important to be able to put numbers to predictions. When evaluating predictors, we compare their accuracy to the overall distribution of nouns over the gender values. So a predictor is only worth something if it performs better than the baseline of 45% of feminine nouns. Our methods for semantic and phonological representations follow the tradition of the analogical principle, which formally started with Bybee and Slobin's paper on English, and which says that words which are semantically or phonologically similar will belong to the same class. This work is also what inspired Köpke to pursue his work on German gender. Thus, we represent the semantics and phonology of nouns as their similarity to other masculine, feminine, and neuter nouns. The approach using vectors is based on Firth's idea about distributional semantics, that the meaning of a word is given by its neighbors. The table shows a toy example of the distribution of 3 nouns, dog, hyena, and cat. The idea is that dog appears in an imaginary corpus once with runs and 5 times with barks. Hyena once with runs and twice with barks, and cat 4 times with runs, and never with barks. From this distribution, we can represent the meaning of these 3 words as vectors, with 1 dimension for runs and 1 dimension for barks. In this corpus, the vectors for hyena and dog are more similar to each other than they are to the vector of cat. The idea is that words which have a similar distribution in a corpus have similar meaning. We can use semantic vectors to represent and calculate the semantic distance between words, in this case, using the cow corpus. In our approach to phonological distances, we use right edge-weighted Levenshtein distances. We count how many differences there are between 2 strings, but we weight each distance at a distance to the right-hand side edge. In this case, Baum and Bauch differ in 1 segment, and that segment is the first one counting from the right. This gives us a distance of 1. The words Baum and Zaum also differ in 1 segment, but the segment is the 4th counting from the right. Thus, we have a distance of 0.25. Instead of finding rules manually, we use a boosting tree model, which is one of the best classification techniques there is. We build many small decision trees and then join them together into a stronger system, which learns automatically all the rules and their interactions. Our predictors are the semantics based on lexical meaning, such as sex and animacy, and semantics based on distances to the 5 nearest masculine, the 5 nearest feminine, and the 5 nearest neuter nouns. Phonological distances and the morphological predictors, derivation and inflection class. To illustrate how boosting trees work, there's here is a toy example. In this task, we want to classify each observation as being a circle or a square. These would be our toy genders based on their position on the X and Y axis. These would be our toy predictors. Boosting trees approaches this problem by doing multiple iterations and at each iteration building a new classifier to solve part of the problem not solved by previous iterations. At the first iteration, we build the model F1, which says if X is smaller than 1, then circle, otherwise square. This model captures 2 observations correctly, but it makes 3 errors in red. At the second iteration, we build model F2, which says if Y is larger than 4, then circle, otherwise square. And we add F1 and F2 together. This combination now makes 1 mistake in blue. At the last iteration, we build F3, which says if X is smaller than 5, then circle, otherwise square, and we add all the 3 models together. This combination covers all cases. This is a toy example because in this case, the models are decision trees of only 1 node. In reality, each decision tree can have many nodes. On to the results. The overall accuracy results show clearly that the system is anything but arbitrary. The combined factors reach a predictive success of 96%. This is the top line in this figure. In fact, the top 2 models, that is, all predictors and all predictors except the derivation, perform equally well. Derivation is essentially irrelevant once we have the phonology. But there is at least some non-overlapping information in the other predictors. This is important because it shows that they all contribute, they're all relevant. Note that the majority case baseline is 45%. This is the accuracy a model would achieve by predicting the most frequent class. So any model with an accuracy over 45% is performing better than a model just predicting feminine. As far as single predictors are concerned, phonology is best. Inflection class is decent. In fact, it is the best predictor for simplex nouns. Semantics is less good, but it works really well for humans. Note that our semantic distances are much better in their performance than semantics based on lexical meaning. Finally, derivation is weakest, but still above the baseline. we can calculate a variable importance estimate from the overall accuracies. For example, to calculate the variable importance of the phonology, we subtract from the accuracy of the full model the accuracy of the model without the phonology. So in this case, 0.96 minus 0.91 equals 0.05. Doing this for all four predictors, we see that the phonology is clearly on top. This gives us a measure of what percentage of nouns only that one predictor can cover. So for 5% of nouns, we need the phonology. But this does not tell us anything about overlap. There might be many nouns which the phonology gets right, that other predictors would also get right. We might call this additive variable importance. We ignore overlap of predictors. Multiple predictors can point in the same direction. This is in line with an approach where assignment principles can reinforce each other. Another way of looking at predictors is what we might call subtractive variable importance. Here we try to eliminate all redundancy. We only include a predictor if it does something that no other predictor does. This is in line with an approach where assignment principles are set up in a parsimonious way. This is subtractive variable importance now. For each predictor, we see the number of nouns that remain when we remove from the dataset all nouns covered by the other predictors and the number of nouns that the predictor under scrutiny predicts out of the remaining nouns. So the phonology can predict another 1,201 nouns out of the 1,584 nouns not correctly predicted by the other predictors. Now we can be sure that we need the phonology only for these 1,201 nouns, or other nouns that the phonology might cover are also covered by other predictors. For Köppchen-style phonological rules, we first run all models except the phonology, which again leaves us with 1,584 nouns. The Köppchen rules correctly predict 3 additional rules, which makes them inferior to our distance-based phonology predictor, which correctly predicts another 1,200 nouns. Finally, a quick word on nested generalizations, where combinations of criteria make a prediction which neither of the individual criteria are capable of making on their own. This is a simple example of such a nested generalization based on the overlap diagram that you've seen earlier. Ensign schwa predicts feminine, as you can clearly see from the figures here. This particular inflection class, however, predicts masculine, and both together predict neuter. So at the end, this is the point about ender. It is a noun for which, by combining all these pieces of information together, we get a single clear and unequivocal gender value that we would not have been able to predict by looking at the individual predictors. To get an idea of how important nested generalizations are in German, we take the full data set and sequentially remove all nouns correctly predicted by the predictors whose interactions we want to examine. So in the first row in this table, this would be the semantics, then inflection. Total remaining is the number of nouns not correctly predicted by either the semantics or the inflection. Number of nouns predicted is the number of additional nouns predicted by both the semantics and the inflection together. This is the most important interaction. It covers approximately 1,000 nouns not covered by the semantics and the inflection alone. Two-way nested generalizations are relevant for about 6% of German nouns. And we went on to do this for three-way nested generalizations as well. The column total remaining shows the number of nouns which were not correctly predicted by the models using one predictor and the models with two-way interactions. The column number of nouns predicted shows how many additional correct predictions the model with the three-way interactions can make from the remaining nouns. So in the first row in the table, we first check the semantics, then derivation, then inflection, then all two-way combinations of these three factors, and each time remove correctly predicted nouns. 1,050 nouns remain, of which the combined model can predict an additional 27. So we see little evidence of three-way interactions being relevant for German. Finally, our conclusions. The German gender assignment system, while complex and unusual, represents a typologically well-known type, a combination of a semantic core and formal, that is, morphological and phonological assignment principles. We see increasingly clearly the interlocking regularities of the system, and we hope to reduce the ill-informed comments still made about German gender. Second, we make a larger point by showing how typologists can benefit from data mining. In earlier work on gender assignment, there was an emphasis on distinguishing regularities from each other to establish which was responsible for a particular assignment. The current work takes a broader view of interconnected and mutually reinforcing regularities. And for this, German indeed is a typological gem. And finally, our conclusions relate to German gender, but we also make a larger point by showing the benefits of the collaboration. Thank you very much for your attention. The bibliography is available in the slides. Thanks.